Thanks very much, Joss, for that introduction. Good afternoon, everyone. You are allowed to go to sleep.
No, you are not.
I've put a title up here, Climate Change, Lakes and the Role of Paleolimnology. And a little outline first. Before I move on to talk about paleolimnology and the evidence that we can find from paleolimnological studies of climate change in the past and at the present time, just a little bit about climate variability in the past, then moving on to the evidence that we have for recent change in lake systems from remote regions, looking in the Arctic and looking at alpine regions. And then the third element of the talk is related to interactions with pollution, coming back to issue not so much of eutrophication in my presentation, because everyone else has been talking about eutrophication, but to focus on a case study of acidification and recovery from acidification, and then finish off with some implications for the Water Framework Directive. I'm sure most people are familiar with paleoecological, paleolimnological techniques, but just a very simple introduction as an introduction to some of the data sets that I'll be showing later on in the talk. The idea of taking lake sediment cores, especially the very recent sediment from lakes with an intact mud-water interface, so we can look at the past and come up to the present day through time. Lots of different techniques can be used, but the technique that I'll be mainly talking about and that we use mainly in our lab in London is datum analysis, and this is just a picture as you see, of a sediment sample where the organic matter has been digested and it leaves behind silt and clay particles, and as you can see, diatom valves, some intact, some broken. And these are excellent water quality indicators. And by looking at the different compositions of diatoms in sediment cores through time, we can reconstruct what kinds of environmental changes are being taking place in that lake system. So to start with just a little bit of context, a lot of the discussion about climate change is about what might happen in the future. Experiments, of course, are to do with what might happen in the future, plus 2 degrees centigrade, plus 4 degrees centigrade that Brian was talking about, or the space-to-time substitution that discussed this morning, looking at places which are warmer at the present time as analogues for the future in places which are currently colder. When we look in the past, we need to have a context. How far in the past do we go? What's the context that we need? What's relevant, in fact, for this particular question? And we might say the Holocene is perhaps the context of climate change, aquatic ecosystem sciences. This is just to show the context over a period of about 50,000 years, and we can see here this rather rapid increase in temperature at the end of the last glacial period and the start of what we call the Holocene, which is the last 11,500 years. It's the period during which people have spread and developed, and agriculture has been developed, of course, and industry has been developed as well. And we can focus perhaps even more on the last 1,000 years. And when we look at the last 1,000 years, one of the iconic figures of climate reconstruction is this one here. It's sometimes been called the hockey stick in the past. This is quite an old figure now, going back to IPCC report in 2001. And what it attempts to do is to show the context of recent warming from the instrumental record here in red against a 1,000-year record of reconstructed temperature using lots of proxy indicators, things like ice cores and tree rings. And what quite clearly it shows is, this stands for medieval climate anomaly or medieval warm period in Europe and the Little Ice Age here. What it quite clearly shows is this cooling trend over the last 1,000 years before the more recent warming, which is related to the extent to which the Earth changes its precessional orbit around the Sun, and we're in this long-term cooling period. But it also shows this shorter timescale variability here, which is on a multi-decadal or centennial timescale, which a lot of people relate to solar variability, and there's quite a lot of evidence to suggest that solar variability does operate on these timescales and can have these kinds of effects on temperature. But also the third natural cause of climate variability is just indicated here, but there are lots of them, and this is to indicate the incidence of volcanic eruptions where dust from volcanic eruptions enter the stratosphere and can cause cooling for a number of years. You don't see it in the mean trend here, in fact, but if you look at this minimum temperature there. This is Tambora of 1815, which depressed temperatures for quite a number of years. So these are the natural reasons why we might expect the climate system to change, and we might ask the question, to what extent have these changes been reflected in lake sediment records up to the present time? Or we might then also ask, of course, to what extent can we identify this most recent increase in temperature, which is, one would argue, is related to the greenhouse gas emissions and global warming from anthropogenic sources. Well, just picking up that first point, the long-term cooling or the change over the whole Holocene timescale, there is strong evidence that that has had major impacts on aquatic systems, especially in low latitudes. And this is just an example. I think most people are probably aware of this, that the Sahara, 7,000 or 8,000 years ago, was full of deep freshwater lakes. And if we look at lake sediment records in the North African, East African region, we can see, for example, from these two lakes here, work of François Gas many years ago, how there's been this gradual decrease and then rather sudden decrease in lake levels, punctuated by lots of dry spells. And here you can see this major desiccation that took place and created the Sahara 5,000 years ago. On shorter time scales, the work of Dirk Verschuren in Lake Naivasha, one of the small lakes in Lake Naivasha, the Crescent Island Crater Lake, again looking at natural variability, and he related in this Nature paper of the last 1,000 years or so a relationship between sunspot activity, which is a surrogate here for solar variability, and lake depth. So water levels reflecting both long-term change and also this decadal centennial variability in solar variability. And of course this is interesting not just to show the sensitivity of these systems in low latitudes to climate change, but it's also important because if we exacerbate the reduction in precipitation and increased evaporation that we're expecting from climate change, then these already vulnerable systems will suffer even more in the future. If we move to more temperate latitudes, then we don't see quite the same dramatic effects on these Holocene type scale climate change or the solar variability change. Work that we've done in our lab in Scottish mountain lakes, as you can see here, just shows this kind of variability over the last 4,000 years. And you see the oscillations here, which are just oscillations in organic matter in the sediment core, probably related to variations in primary production and preservation of organic matter in these kinds of sediment cores, and possibly related to solar variability, but this is not in any way proven. But you can see, compared to in low latitudes, we have rather more stable situations over that Holocene period. So the key question then is, what about the more recent period? And when we talk about the most recent period, of course, we're talking about greenhouse gas increases, and the best evidence for the way that greenhouse gases have increased globally come from a combination of the Mauna Loa carbon dioxide record, which goes back 50 or 60 years or so, shown here in blue, connected up with the record of measurements of carbon dioxide in bubbles of air trapped in polar ice cores, in this case from the Antarctic. And when we do that, as you probably know from IPCC reports, we can go back to something like about 1750, 1760 or so, back to what we might call pre-industrial baseline concentrations of carbon dioxide of about 275 parts per million by volume. And we're now about 385 and increasing. And it's this inexorable rise in CO2 concentrations against this relatively stable background that, of course, gives real cause for concern. We might expect that we should be able to see lots of evidence for this impact on the temperature system and also on the effects on ecosystems from our sediment records. Well, the problem is that the impacts on lake ecosystems in particular, so far as we can see from sediment records, are really slight. And that's mainly in populated parts of the world because we have still dominant impacts from other kinds of human activity, such as eutrophication that we heard so much about this morning. And if we take don't worry about the detail here, but if we take a sediment core from Esthwaite water in the English Lake District, that is one of the most eutrophic lakes in the Cumbrian Lake District, then we can see the impact of eutrophication and the difficulty of picking up anything to relate it to climate change. So here's about the turn of the 19th century, 1890, And all this change here, as you can see in the species composition, above that, since that time, above that line, is related to the increasing eutrophication of that system. Below it, we might argue that this is variability, not so much variability, but variability associated with natural climate change. So here we have an enrichment pair and possibly climate-driven changes before. But because of the dominance of the enrichment, because of the dominance of the nutrient loading, it's very difficult to see the impact of climate change in the past up to the present day. But I'll come back to this later. Again, acidification is another dominant driver of ecosystem change, particularly in the uplands in northwestern Europe. And again, a diatom diagram, rather an old diatom diagram in this particular case, showing the effects of acidification. And it comes from the round loch of Glen Head, which is a lake in Scotland. And you can see, going back to, again, to the mid-19th century or so, we have rather stable communities here. And then the impact of acidification over the last 150 years, totally changing the structure of the diatom composition, but changing the whole ecosystem functioning as well. And we can see in particular, in terms of species, this one here, which is very indicative of very acid waters, becoming dominant in the lake and very rare prior to acidification. So because of these human impacts in the lakes in Europe, in populated parts of Europe, it's very difficult to see the climate signal. And it's forced a lot of us to look at more remote regions of the world, into the mountains and into the polar regions, to see whether we can see change which has been caused by climate that is not related to other kinds of human activity. So just some examples of that. Some of the pioneering work has been done in Arctic Canada by John Small and his group in Kingston, in Ontario. This is one of the first papers that made the headlines back in the 1990s, but there's been an enormous body of work in that region since by his lab and by people who've moved on to other labs but started off in his group. And you can see here evidence well, you can't see the evidence, but you've got to believe me that this is the explanation given by the authors, that we have lakes here which are having less ice cover in the summer, not the winter in this particular case. These are lakes that might be frozen completely during the summer, but with warming, now they melt to some extent, leaving a moat of water around a floating island in this particular case. And here's a diatom diagram showing rather dramatic changes in the composition of the diatoms at the top of this sediment core. This particular species here, a Pinularia species, is one that's associated, it's an epiphyte, and it grows on aquatic mosses. And so one can imagine that as the littoral habitat increases with melting of ice, the development of aquatic mosses, and a habitat suitable for the growth of epiphytes. And here one can argue that this species here, which explodes in the last few decades, is indicative of climate warming. And more perhaps important, it suggests that this is unprecedented climate warming, because although there's no dating on this, this almost certainly covers a number of centuries, if not millennia, of timescale. And we don't see any evidence of that change in the previous period. Coming to Europe and looking to the mountaintops, and we've been involved in lots of European projects on mountain lakes. And this is work of Jordi Catalan from Barcelona and his colleague Sergi Pla. Again, it's a diatom diagram here. It's going back a couple of hundred years, and you see the red taxa here. These are benthic diatoms, not showing any real species change through time. The main change, of course, are the ones in blue, and this is a development in the last few decades of a diatom phytoplankton. And this particular species here, Jordi Catalan and his colleagues have been following in Lake Rado in the Pyrenees, showing that it's most abundant in the October and November period. And has argued that there is a strong reason to suspect that this is related to warming of the water, especially in the autumn period, extending the stratification period, delaying the date of overturn, and delaying the onset of winter ice. And that's allowed this plankton development to take place. Whether there's any nutrient loading associated with this is a moot point, but the argument here is that, as we were discussing this morning, even these remote mountain lakes, we've got symptoms of eutrophication. And then a colleague of mine, Nadia Solovieva, working in Russia, in Arctic Russia, near the Ural Mountains here. Again, a similar kind of diatom diagram, a very remote site, but in the last 20, 30, 40, 50 years or so, there's been an increase in this particular diatom plankton, Asteronella formosa, which again suggests a nutrient enrichment, probably directly related to global warming, temperature warming. And again, a eutrophication symptom. So from these kinds of lines of evidence, which suggests that we do have impacts of climate change in these remote regions, it really means that we should reinvestigate very carefully the changes that have been taking place in the very recent sediment records of our eutrophication suffering and acidification suffering lakes in Europe. And particularly ask the question, could climate change be influencing attempts to restore polluted lakes, e.g. with respect to the Surface Water Framework Directive? So I want to just give an example here of surface water acidification studies that we've been involved in to ask that question, to what extent is climate change perhaps now beginning to confound attempts to restore acidified lakes? Well, if this were the story for climate change, we would be all very happy. This is a story for sulfur dioxide in Britain, but it's the same picture across the whole of Europe, and it's a story of strongly declining sulfur dioxide emissions down to this target level by 2010. Britain, in fact, will be below the target by 2010, probably the first time Britain's actually achieved such an astounding environmental success. It's not all good news, because for nitrates, nitrogen oxides, there's been a significant reduction, but in fact by 2010, the target date, Britain won't quite have reached that particular target, but a substantial reduction in the emissions of acid acidifying gases. So you might imagine then that we should be able to see the response to this in the lakes that we've been monitoring over the last 20 years or so. And indeed we do. The first evidence we would expect will be a decline in the sulfate concentrations in the water, because the sulfur emissions have gone down very dramatically, the sulfur deposition has gone down very dramatically, and we can see that in almost all our study lakes here, 22 lakes and streams across the United Kingdom, we have declining trends in sulfate, some more than others. Two lakes I'm going to pick out here. One is a Welsh lake called Clanclaggy, which is this one here, and the other one is Round Loch of Glen Head, which is this one here. Substantial decreases in sulfate. That's good news. We might expect then for the pH to increase, because this acid anion has decreased. And in fact, we do get good evidence for pH increase across the network. Again, you see these increasing pHs at the formerly acidified sites. And here's Clanclaggy, strong increase in pH, and the Round Loch of Glen Head, the same. Then we start looking at the biological response to these hydrochemical changes. Again, we can see very positive news. This is the diatom epilithum. These are not diatoms in the sediment cores now. These are diatoms collected from stones around the edges of the lake that we've been monitoring for the last 20 years, 1988 here to 2008. And again, this is a site which is improving in terms of its pH. We can see that this species here, that was a dominant in the lake at the maximum acidity, is declining gently over that period of time. This is Tabularia quadriceptata here. And it's been replaced by especially this navicular species, Navicular leptostriata, as you can see here. It's become now the most abundant species in the lake. What's interesting, however, is that although Tabularia quadriceptata was in the lake before at the most acidic point and was very, very rare previously, Navicular leptostriata is not quite a new species, but it's now much more abundant than it ever was in the past. To link that then to the sediment core story, and I showed a diatom diagram from the Round Loch of Glen Head sooner, we can't directly connect the epilithic data to the sediment data, because there are different habitats for diatoms growing in a lake. And so the way we've been following the diatom populations in the lake so that we can match it up with the sediment record and go back further in time to the 19th century is by using sediment traps. So we can expose sediment traps in the lake here. We can empty them every year. We can look at the diatom content. The diatom assemblage here then is mixing the communities from the whole lake, and then they become analogous in terms of their composition to the diatoms accumulating in the lake sediment. And when we do that, we can then add the data from the sediment traps, which are shown here, 20 years of sediment traps with diatom changes, to the core. This is the same core we saw before, but it's rotated now through 90 degrees. Here's that acid-indicating species, pretty much absent in the pre-acidification period. This is a reference community, you might argue, the acidification, the development of this quadriceptata, and then in the sediment traps, a general decrease. And here the navicular leptostrata, the one that's increasing. And this is 2005. In the last 3 years, it's continued to increase. And this is the interesting point, is one that so far we don't have any sign of the reference community coming back. We haven't been so successful at this site so far. But secondly, the species composition is different at the moment from the species composition we might expect for the same level of pH during the acidification phase. And what we can do is to look at this in ordination space to show the distances between the reference community and the present day, and the direction in which the composition is changing at the present day. So here's a round off of Glen Head. All the points here, there's points from 120 low alkalinity lakes in the UK where we've done diatom analysis from. So this constrains the data and the diatom assemblages from the core and the sediment traps. And the bottom of the core, around about 1850, is located here in that species space. And this is what we would call the reference. As it acidified, it moves to this place here, and all the blue are the sediment trap data. And we've come back a little way, not very, very far, as you can see, and because of the navicular leptostrata, the trajectory is moving somewhat away from the back trajectory back towards the reference condition. Just another example, and we can do this for many lakes. Claggy, this lake in Snowdonia in North Wales. Not so many data points here, but you can see the reference community in the 19th century, the acidification. Here's that same acid-indicating species and massive development of it. On the recovery phase, you can see, again, a very rapid reduction in the abundance of that particular species, which is what we might expect to be going back in that direction there. But again, we have Tabularia flocculosa here that is increasing in abundance, whereas in the past, in the sediment record, it was not so important. You might think these are minor changes, but they're very interesting changes. And we can begin to ask the question, to what extent should we be farther back towards the reference, given the changes in acid deposition that's taken place? And to what extent should we be expecting to go back down the same trajectory? Or in other words, how can we explain the fact that perhaps we're moving into different species compositions from the ones that we had before? And there are many hypotheses, and I don't have answers to these yet. This is an active area of research, but we might say there's lots of change occurring by chance. There's hysteresis perhaps taking place, where we perhaps will move back to the same kinds of composition, but with a delay and going through a different route. All kinds of internal ecological rearrangements that might have taken place to explain these changes in species composition. These you might call internal hypotheses, but externally we also know that nitrate is breaking through and the soils are being saturated and nitrate concentrations are increasing at this site. We also know that in fact the water is warming. So we have these two other factors to take into account, not just the reduction in acid deposition. So we can say, well, to what extent might this have implications for the Water Framework Directive, where the reference condition is sometimes defined as the pre-acidification reference state defined paleoecologically, but it would even apply also to a reference condition of an analog lake in space. In an ideal world, we would expect this kind of trajectory. We go back to the past. We put here high, good, moderate, poor, and bad. The Water Framework Directive boundaries, this could be 150 years or so ago, the gradual acidification, or it could be eutrophication to some maximum here before the attempts to mitigate these pressures, decreasing pressures into the future, and hopefully a recovery to more or less the reference conditions that we've defined historically. What, of course, is happening at the present time is that it's not possible to go back to such perfect quality, to that historical semi-pristine condition. Measures are taken to improve the water quality, but in particular to get the lake back to at least good status, which would be a target somewhere about here. But of course, climate is changing the whole system, the whole way the system behaves. And so it's not necessary that we can achieve what's already been defined as the target. And so instead of getting to the good status here, in fact, by present measures, if we have a change in the baseline, it means probably that the high status that we had in the past cannot be achieved in the future. And it means that the measures that we've already taken will not be as effective in achieving that particular status. And this is very analogous with Eric and Brian and everyone this morning, in fact, saying that for eutrophication, the important thing, of course, is to carry on reducing the nutrient loading. And the nutrient loading will have to be reduced even more to cope with the effects of climate change. So the problem here is that if we continue with existing measures, the measures that have taken already, instead of ending up with a moderate status in this example, a good status would actually then lead us to be achieving only moderate status. The only way to get from here to there is by intensifying those measures. But of course, there is one other way to do that, and that is to do this, to shift the goalposts. And it may well be that whilst in some cases we can intensify the measures and achieve that good status, in other cases it may be absolutely impossible to do it. And certainly with acidification, it's very unlikely that we'll be able to go back to high status as currently defined, especially if lakes become more naturally acidic because of increased winter rainfall and increased sea salt deposition from the Atlantic, which releases hydrogen and aluminium ions from soils. And so this is a more complex future that we have to look forward to. And it becomes increasingly important for policymakers to realize that climate change will have major implications for the implementation of the Water Framework Directive. I'll leave you with the conclusions, but thank you very much.
Thank you very much, Brian, for taking us back in the past to bring us further in the future with predictions. And well, the issue of the shifting baseline is something that appeals very much to me, and we have talked earlier about that. Certainly something to take into account, that we may not be able to achieve the goals of the past because the whole system has changed because of climate. There is time for some questions. Any questions to Brian and Ulrich? Nobody? So it has been so difficult to disentangle these effects from the climate effect from the environmental change effects. Is that also true for disentangling separate environmental changes like acidification and eutrophication maybe taking place at the same time? Or have you been able to find always the right sites where only one was operational?
I mean, the trick in this kind of research is to try to use the natural distribution of lakes and lake types as a laboratory and to avoid, to begin with at least, where there are real complications. But I think looking to the future now, we really do have major complications because nitrogen deposition, we know, is going to cause, and probably is already causing in our upland sites, eutrophication as well. So there are lakes, certainly in Britain, and maybe in many other parts of the world, where we have increasing nitrate concentration acting as a nutrient. There's been quite a lot of bioassay work to show that if you add nitrogen, in fact, you can get increased algal biomass as a result. So some of these lakes are, in fact, either co-limited with phosphorus or are nitrogen limited. So we're going to have a very complex future, I think, really, with climate change, with changes in acidity, and with the changes in nutrients. And my take-home message is not just to look at the Water Framework Directive again, but it's the absolute importance of continuing to fund and develop monitoring networks, because I think models will never be sufficiently sophisticated, in fact, really to really predict what's going to happen. I think we've got to have a watching brief whereby we keep our chemical, physical, biological monitoring of key systems going through time.
I think also setting the right goals is important, and to really make them so whatever you can use from your paleoecological studies to relate the baseline to climate issues only, that would help really a lot. If you could find maybe species compositions of diatoms, for instance,
I think it's
according to a gradient.
Yeah, it's very important, I think, to know what we had in the past and the trajectory from the past through to the present day. What I think is increasingly obvious is that we can't actually go back to a condition we had in the past.
Exactly.
So I regard the information we get from the paleoecological record to provide certain kind of benchmarks or evidence of the kinds of changes that might take place in the future, and not necessarily as a way of defining the target. But it seems to me that a knowledge of those pre-pollution conditions and pre-climate change conditions do actually constrain our thinking on what potential targets might be.
Okay. Thank you very much, Rick.